Okay, hello. Today we're going to talk about graphs of exponential and logarithmic functions. You'll need a paper and pencil, and it would also be good to have your computer open to Desmos so that you can access that when I ask you to. Okay, so first of all, we're going to start off with a function from algebra, y equals square root of x. And what I want you to do is graph that on Desmos, and also then graph each of these on Desmos. And for each one of them, I want you to describe their relationship to that y equals square root of x graph. Okay. All right, so I'm going to give you a moment to do that. If you'll go ahead and pause, graph on Desmos, and describe what happened. Okay, so let's take a look at these. This y equals square root of x plus 1, that is related to this y equals square root of x graph by just shifting up 1. Okay. The next one was a shift down 1. These next two were a shift left and right 1. And the last two were reflecting across the x-axis and y-axis. And the thing I want you to especially notice is that the placement of the extra objects, the extra items. Here we had a plus and minus 1. They were located on the outside of the function. Here we had a plus and minus 1 that were located inside the function or with the x. Here the negative was outside, here the negative was inside. And we'll see we can always associate these kinds of placements with certain kinds of transformations. So if we start off with a function y equals f of x, and we do a plus or minus c on the outside, then that's going to be a shift up or down. If we do a plus or minus c inside with the x, then that's going to be a shift left or right. And notice that the plus c on the inside is left, which may be opposite of what you think. And then a minus outside, reflection across the x-axis. A minus inside, reflection across the y-axis. Okay, so now let's apply some of these lessons to the exponential function. First, let's just remember some facts about the exponential function. So when x equals 0, if we have this exponential function y equals b to the x, we plug that in, we get y equals b to the 0, which is 1. So we got x is 0, y is 1. And so we have this special point 0, 1 on the graph. When x equals 1, we put in x equals 1 here. We get y equals b to the 1, which is b. Anything to the 1 is just itself. X equal 1, y equals b, so the point 1b is on the graph. This y equals b to the x graph is increasing. It's going up as you go from left to right. And the function has a horizontal asymptote, y equals 0. This is the same as the x-axis. The function gets very, very close to that asymptote. And so as an example, if you'll graph y equals 2 to the x on Desmos, look at these special points 0, 1 and 1, 2. Notice that b is the base, which is 2 for this function, and the asymptote y equals 0, and see that everything looks the way you would expect it to look. So go ahead and pause this and do this graphing. Okay. Now let's take this 2 to the x function, and on your paper I'd like you to write down the equation that would shift this graph up 1 unit, the equation that would shift it down 1 unit, left and right equations, and reflection across the x and y axis equations. All right, so just as an example, shifting up 1 unit would be 2 to the x with the plus 1 stuck on the outside. Okay, so pause this now and try to do the rest of these. Okay, here are the answers. Shift up 1, down 1, left 1. Notice that the plus 1 is in the exponent with the x. Right 1, the minus 1 is in the exponent with the x. Reflect across the x-axis, negative outside. Reflect across the y-axis, the negative with the x. Okay. And so one thing that we'll be particularly interested in is what happens to the asymptotes with these kinds of shifts. Does the original asymptote move or not? Remember, the original asymptote was right on the x-axis. And so if you'll sketch each of these on your paper, just do a really rough sketch and tell me whether the asymptote moved. So this is that 2 to the x shifted up 1, down 1, left 1, right 1. Reflect over the y-axis, reflect over the x-axis. Do those 6 sketches and tell me whether the asymptote changed from the x-axis or stayed on the x-axis. After you do those sketches, check your answers by graphing each of these 6 on Desmos. And so I'll give you some time. If you'll pause this now and do that, we'll say what happened. Okay, so let's check your answers. For the vertical shifts up and down, you notice the asymptote moves along with the function. So the shift up 1, the asymptote moved from y equals 0 to y equals 1. The shift down 1, the asymptote moved from y equals 0 to y equals negative 1. And all of these other shifts left the horizontal asymptote unchanged. It stayed at y equals 0. The function moved, but the asymptote stayed the same. Okay, and that makes sense because like a left shift, you pick up that horizontal asymptote and move it to the left. Well, it's infinitely long, so when you do that, it lands right back on top of itself. And similarly, it makes sense for all these other ones why the horizontal asymptote would not change. Okay, now there's a couple other kinds of transformations. We can multiply by a number c outside of the function, or we can multiply by a number c inside of the function with the x. And those are stretches, either vertical or horizontal. And those kinds of stretches don't affect the asymptote, as you can check if you graph these 2 functions on Desmos. So here we're multiplying by 3 outside the function. Here we're multiplying by 3 inside the function with the x. So I'll give you a moment, pause this, and graph these on Desmos and see that the horizontal asymptote did not move. Okay, so here's a summary. For any transformation of y equals b to the x, this exponential function, the horizontal asymptote is only affected by a vertical shift up or down. Also, the function approaches the horizontal asymptote in one direction and bends away from it towards positive or negative infinity in the other direction. So this is very important for us, because putting these 2 things together, we see that we can graph any transformation of the exponential function by doing 2 things. First, finding the horizontal asymptote, and second, finding 2 special points on the graph. These will correspond to the easy exponent values 0 and 1. Okay, so let's do an example where we put all this together. Here we've got this function y equals 2 times 3 to the 2 minus x minus 4. And we want to do 3 things. Find the horizontal asymptote, find the 2 special points, and sketch the graph. Okay, so this could be a good test type question right here. And you'll notice that this is just a transformation of the exponential function y equals 3 to the x. And we'll figure out how to graph this. All right, so first of all, the horizontal asymptote. Most of this is irrelevant to the horizontal asymptote. It's only the vertical shift up or down that affects that. And we see that this negative 4 is the only thing affecting the vertical shift. So the horizontal asymptote is quite simply y equals negative 4. Okay. Now let's talk about how to find the 2 special points. So one of these occurs when the exponent is 0. So we set the exponent equal to 0, and the exponent was 2 minus x, right? So here's this exponent, 2 minus x. We set that equal to 0 and solve for x. And the exponent is 2 minus x. Add x to both sides, we get x equals 2. Now to find the y value, we're going to substitute this x value into the function. All right, so here's the function. We replace the x with this x value we found, 2, and we just start calculating. 2 minus 2 is 0. That's no surprise. We wanted the exponent to equal to 0. Now it is. Now we do our order of operations, of course. Exponent first. 3 to the 0 is 1. Anything to the 0 is 1. Multiplication next. 2 times 1 is 2. 2 minus 4 is negative 2. So we've got this point where x equals 2 and y equals negative 2. So the point 2, negative 2. The other special point happens when the exponent is 1. So first we'll find the x value where this happens. We want the exponent to equal 1. Again, 2 minus x was the exponent. We set that equal to 1. And we solve, we add x to both sides, subtract 1 from both sides, and we get x equals 1. Now we'll substitute this into the function to find the y value. So here was the function, replace x with 1. Do this subtraction, 2 minus 1 is 1. We get an exponent of 1. Again, no surprise, that's what we wanted the exponent to equal. Now we do our exponentiation. 3 to the first is 3. Multiplication, 2 times 3 is 6. 6 minus 4 is 2. So here's our other special point, 1, 2. Okay, so here's a summary. We knew the horizontal asymptote was y equals -4 because the vertical shift was the only thing that affected that. Here's our two special points, 2, -2, and 1, 2. And then we're going to do a sketch. And so I've started this sketch. Here's the horizontal asymptote, y equals -4, shown as a dotted line. Here's the 2 points, 2, -2, and 1, 2. And to sketch the curve, we see that we have to decide which direction this function approaches the asymptote and which it goes off to infinity or -infinity. And we look at the relationship of these 2 points. And we see that this point's closer to the asymptote, so that means the function must approach the asymptote over here and come up through this point and go off to positive infinity in this direction. And when we graph the function, we see that's indeed what happens. So really, just by knowing the horizontal asymptote and the 2 points, we're able to know exactly what this exponential function does. Okay, so when I'm grading your sketches that you'll do on your test paper, I'm going to look for these 3 components. First of all, the horizontal asymptote shown as a dotted line, the 2 special points accurately plotted, and finally the curve sketched correctly with arrows on the end showing that the curve continues. So I couldn't do this in Desmos, but you would need an arrow here to show that the function continues going up, and you would need an arrow over here to show that the function continues going to the right that way. Okay, so